Have you ever gazed at the twinkling canvas of the night sky and pondered how scientists measure the mass of stars that gleam light years away? Direct measurements are impossible. We cannot place a star on a scale or visit it to swipe samples. Despite this, astronomers assert with confidence that certain stars have masses that are multiples of our sun's weight. How can they accomplish this seemingly impossible task? The answer lies in the paradox of astronomy, weight measuring without touch. The secret unto this marvel is rooted in gravity, nature's steadfast constant. Every object with mass generates its gravitational pull. Stars, planets, and even tiny meteoroids exert gravitational forces on one another, dictating their celestial ballet. By observing these orbital motions, astronomers can decode the strength of the gravitational influence at play, which allows them to indirectly compute a star's mass. Much like gauging the weight of a passenger spinning on a merry-go-round, the movement of celestial bodies reveals the hidden masses lurking within the cosmos. One of the simplest yet remarkably effective means to determine a star's mass is through binary star systems, where two stars orbit one another in a cosmic dance. Surprisingly, over half of our galaxy's stars are part of such pairs. As these stars revolve around a shared center, their separation and velocity create identifiable patterns. By carefully tracking their movements and distances, astronomers apply Kepler's laws alongside Newton's laws of gravity to deduce their masses. The underlying notion remains accessible. A heavier star produces a stronger gravitational pull, compelling its partner to move more rapidly around it. This approach is so reliable that it lays the groundwork for mass measurements throughout the universe. Yet what about the solitary stars that glide through the galaxy without companions? For these independent giants, scientists harness the sophisticated method of stellar modeling. Characteristics such as brightness, temperature, and even the pulsations. Yes, stars resonate like musical instruments, help reveal the internal architecture of these luminous spheres. The vibrations, analyzed through the field of astroseismology, provide insights into the star's density and ultimately its mass. It resembles discerning the thickness of a drum skin by the sound it emits. Stars hum their secrets, and astronomers decode their weight through these cosmic melodies. Additionally, the waltz of planets around stars offers more data. A planet's orbit doesn't merely revolve around a star, it causes the star to wobble in response, albeit ever so slightly. By examining the speed and pattern of this subtle wobble, astronomers can infer both the planet's mass and the mass of its host star. Visualize a towering parent gripped by a small child, merrily spinning. Both bodies feel the effect of the dance. Thus, by detecting the star's wobble, its weight is unveiled. Even the very light radiating from stars narrates stories of their mass. Through the process of fusion, stars maintain a delicate balance between inward gravitational forces and outward fusion pressure. This relationship determines their brightness, creating a correlation whereby brighter stars are generally heavier, while those that twinkle with dimmer light tend to weigh less. By juxtaposing the brightness of an isolated star to the masses of thousands of neighboring stars, astronomers unearth additional layers of understanding in this quest to measure and comprehend the universe.